So last lesson we talked about simple interest, which we said is not really that realistic. It doesn't get used to calculate the amount of an investment or of a loan. And today we are on 7.2 compound interest. Compound interest is a much more real-life-like example. And we just have a couple notes right up at the beginning. So we're going to take a definition of compound interest on page 8. Compound interest is interest that is calculated at regular compounding periods. So in simple interest, you only gained interest on the principal. In compound interest, the amount that's in the account will, the entire amount will get paid interest on. So the next little note is added. Let's do it this way. This interest is added to the principal. This interest is added to the principal for the following compounding period. So your interest also gets compounded, gets interest on it. We need to know what a compounding period is then. Compounding period is the time interval after which compound interest is calculated. The time period, the time interval after which compound interest is calculated. So if you put $1,000 in your account today and pull it out tomorrow, you won't accrue any interest depending on the compounding period. If the compounding period is daily, then you will. If it's monthly, you won't. So it happens at the end of that period of time that it's in. So if it says it's going to compound monthly, then it needs to be in for a month, that kind of thing. Okay?
It doesn't do like gradually to that percent?
So in real life, at a bank, yes. If it says 12% per year, or that's too high, let's say 4% per year, then they actually take that 4%, it gets divided by 365, and every single day interest is calculated. Does that make sense? Mm-hmm. Like if you owe a loan, then that interest is calculated. They'll give you a statement, like they'll charge your account monthly, but if you only borrow it for 7 days, it doesn't mean you don't have to pay interest on it. You have to pay interest for those 7 days. Yeah? Okay, let's look at your investigation that you have there. We have Alex again from lesson 7.1. He invested $1,000 at 5% interest for 5 years in that simple interest scenario. Alex earned $50 of interest each year for a total of $250 of interest. Okay? That's simple interest. He's only gaining 5% interest on the principal, not on the full amount in the account at the end of each year. Now suppose Alex deposits the money into an account that pays the same annual interest rate of 5%, but it's compounded annually. How does this affect the amount of interest that he will earn? So we have an extra column here. We need to consider the balance at the start of the year and the balance at the end of the year. So first I'm just going to give my years 1, 2, 3, 4, 5. And we're talking about at the end of the year. The first column deals with the money at the start of the year. Then we're going to get our interest earned interest earned. And you can start filling it out already on your own. Then you have the balance at end of year. So again, he's starting with $1,000. We know from yesterday that 5% of 1,000 is $50. So he's going to have 1,050 at the end of that first year, which means at the start of the second year, the principal is now 1,050. So he's going to earn now 5% of that as interest. Does anybody have that? The next number? 1,050 times 0.05. So he's going to get $52.50 that year. We add that up. It's going to get us 1102.50. And now that becomes the starting amount in year 3. So what's 5% of that?
55.125.
55.1, and we'll round up to 13. So then we're going to be at 1157.63, and that becomes the starting amount, the principal amount at the beginning of year 4. 5% of that. And we add that to our 1157.63. $1,215.51, I think. 5% of that.
60.78.
For $1,276.29. So now, what banks will often do, or what an investment company will often do, is say, okay, look, add up the number in this column, and that tells you your total interest earned. And then here, of course, is your final balance at the end of 5 years. Now you put in $1,000, and you now have $1,276 without doing anything. Okay. And we are looking at the fifth and sixth columns that you guys have there. You have a first difference column. So we can find the first difference by taking 1102.50 and subtracting 1050. And same there, same there, same there. What you're going to find out is it actually corresponds directly to the amount of interest that was earned that year. Right? If you take 55.13 and add it to 1102.50, you're going to get 1157.63. So obviously the difference between these two is 55.13. The difference between these two is 57.88. The difference between these two is 60.78. So what have we found out in the first difference column? Are they constant? No. Do you think the second differences will be constant? No, they won't be. Third differences? No. Let's see if there's a common ratio, though. So remember, for a ratio, we had to take this y2 and divide it by y1, right? We have to find the factor that is used to get from one y value to a consecutive y value. So the ratio here would be 1102.5 divided by 1050. And then we do the same thing here, 1157.63 divided by 1102.50. And we continue down the chart, 1215.51 divided by 1157.63. And the last one. And what do we see in the ratio column? describe that. Somebody, anybody. Did we find a common ratio? Yes, we did. Okay. Good. So when we are looking at simple interest, the interest earned per year was the same amount every year. Now we're looking at compound interest, and the interest earned is not the same every year. It's different every year. It goes up every year. It's this column. Okay. How much does it go up by? Well, it goes up by 5%. Why is it 1.05? It means you're multiplying the amount that you have times 1.05. 1 means you're going to get that whole principal back plus 5%. Okay? So the rate is always 1 plus R, this ratio. So this is growing. This is exponential growth. It's growing by 5% each year. Good. Let's take a couple more notes at the top of your next page. Oh, we should, let's go through the questions here. The interest earned column, we said there's a constant ratio increased. What is the advantage of compound interest over simple interest? Can anyone put that into words? What's the advantage of compound interest over simple interest?
You get more.
Yeah, why do you get more?
It adds on to the
Yeah, you're getting interest on your interest, is a way of saying that. So before we were only getting interest on the original principal. Now the interest from 1 year is becoming the principal for the next year. So we're getting interest on our interest with compound interest. We calculated the first difference. What type of relationship is there between the balance at the end of the year and time? So what type of function did we make with a common ratio? What type of function is a common ratio? So if we were talking about sequences in series, it would be geometric. Yep. What type of function from earlier in our experience here this semester? It's exponential. Okay. So we have repeated factors of 1.05. We're taking this initial principal of $1,000. We're multiplying it by 1.05. And then we're taking that number and multiplying it by 1.05 again. And then we're taking that number and multiplying it by 1.05 again. So we're actually taking our initial amount and we're multiplying it by 1.05 to the power of n. Or, I guess, well, we could use n for the number of compounding periods. Right? So it's something like this. But we'll get to that soon. Calculate the common ratios. We did that as 1.05. What does this tell you? Tells us that we're right, it was exponential, and that we're going to multiply our amount by 1.05 every single year. Sketch the graph. And there you have the function there. Sketch a graph for the data given and a graph of A equals 1000 plus 50t on the same grid. So sketching a graph for the data that's given, basically we have our years, 1, 2, 3, 4, 5. And we have our amount. We're starting at 1,000. So I'll go like 500, 1,000, 1,500. My graph is far less perfect than yours will be. And we're just going to plot our points that we have. So after 0 years, we have $1,000. After 1 year, we have 1050. After 2 years, we've got 1102. After 3 years, we have 1157. My graph isn't very good. After 4 years, we have 1215. And after 5 years, we've got 1276. So this graph is going to be fairly linear, but it's actually got a slight exponential growth curve on it. And the idea that you're supposed to see if you also graph the function a equals 1000 plus 50t is that it's the same line. Okay? That's enough for the investigation. If you have some kind of decently drawn, sketched function there, that's sufficient. You should just be able to see that they are indeed the same function, that this data is modeled by that curve perfectly. It's not always going to be a perfect situation, but in this case, the interest earned is guaranteed at 5%, so it will be a nice smooth curve. Okay. The amount of a compound, we're taking notes at the top of page 9. The amount of a compound interest investment or loan can be found recursively. So that means we can think from 1 year to the next year. So if we'll write that down. The amount of a compound interest investment can be found, the amount of a compound interest investment can be found recursively. I'm going to put this in brackets because it's kind of an explanation of what that means. If you know the amount at the beginning of a year, doesn't matter what year, if you know the amount at the beginning of a year, you can determine the amount. If you know the amount at the beginning of a year, you can determine the amount at the beginning of the next year. Right? That's what it meant for to have a recursion formula, is that if you have a certain term, you have enough information to find the next term. So, in order to do that, we let lowercase I represent the annual interest rate. Let lowercase I represent the annual interest rate per compounding period. The amount after one compounding period is determined by adding the principal to the interest for that compounding period. So the amount in the account after one compounding period is the amount that you started with at the beginning of that compounding period plus the interest earned during that compounding period. Okay? So if we want to do this, we can say this is the amount at end of period. This is the amount at beginning of period. And this is interest earned during period. That makes sense. If you start with a certain amount, you add what you earn during that amount, you'll have your new total. Okay? But we can also break down this this interest earned during that period a little bit further, it ends up being, so we have our original principal amount, the interest that you earned, the amount of that interest, the value of that interest is actually the principal that you started with times your interest rate times the amount of time that you've left it in, t being like the number of compound periods. Does that make sense? So the interest that you earned during that period is actually the principal multiplied by your interest rate for the amount of time that you've left it in there. Okay? Now, we're just considering one compounding period, one, in this case, 1 year, or one compounding period. So t is actually 1. Okay, so now look. Let's do this. After one compound period, comma, t equals 1. Well, anything times 1 is just itself. So we're left with a equals p plus pi. Well, we can use our algebra skills to factor this expression. We can pull the p out of both of these terms, and we're left with, if we pull the p out of this factor, we're just left with 1. 1 times p is p, plus I. I times p is ip, or pi. Okay, so this is a way to think about compound interest. This is the amount that's left over. Here's a formula for it. You just take the principal that you're putting in, multiply it by 1 plus I, which, if you think back to our 5% case, is easy to understand. It was just, you don't need to write this, but it was just our $1,000 times 1.05, right? Because our interest as a decimal is 0.05. Add it to 1. So that means the amount left at the end of the year is going to be the amount that you started with times itself plus 5% of itself, or itself 1,000 times 1.05. Okay? Now, the way compound interest works is that we don't just have one period, one pay period. We have several compounding periods. So I'm just going to take this. We're not going to really explore it a whole lot further. We're going to finish these notes and get into examples. What happens is that I'll write it as a sequence. So as a sequence. So the terms in the sequence would be, you'd start with your principal, and then you'd have this, the amount. So this is always the amount. So the original amount is just your principal. The next amount, the amount after the first compounding period, is p times 1 plus I. It's exactly what we have here. After one compounding period, that's what happens. Well, what happens in the next compounding period? We're going to multiply it by this bracket again. So now we have two factors of 1 plus I. In our example, that just meant multiplying it by 1.05 again. Okay, and then if you take that amount and you multiply it by another factor of 1.05, or in the general case, 1 plus I, you now have 3 factors of that. And in the fourth compound period, after 4 compounding periods, you have multiplied it by that rate 4 times. So you have 4 factors of 1 plus I. Is this making sense? You keep going until you get to the end. It just keeps on going. Okay? So what are we trying to say? This is a geometric sequence with first term of A equals P, and common ratio of what's our common ratio? R equals 1 plus I. To find the nth term T of n equals A R n minus 1. And now we can sub in these things that we know. So to find the nth term, we know A is P, and we know R is 1 plus I, and then we have n minus 1 up here. So we've got, and actually, I'm going to backtrack mentally just for a second and change one little thing that we did here. This is the amount before a compounding period happens, okay? So remember we talk about sequences that n is always a whole natural number. So 0, you can't have a 0th term. Does that make sense? This would be the 0th term, and this guy would be the first term. So I'm going to just cross him out for a second, and we're just going to think of this as a sequence where n is the term number. So this is the first term, second term, third term, fourth term. In which case, just here in this note, the first term isn't p anymore. The first term is p times 1 plus I. Hopefully you can fit that in there. And that also means here, if you could just erase for a second, now when we sub in our first term is p times 1 plus I, so that's what's there. And our R is 1 plus I, and then we still have n to the power of negative 1. Okay. Everyone's good with that? Okay, all we did was we changed our first term of our sequence to what's actually our first term, not our 0th term, because sequences don't have a 0th term, they start with the first term, natural numbers. So that changed this, which when we subbed it in here, now we needed to make sure we subbed it a little bit carefully, but now we notice that we have a base raised to the first power and the same base raised to n minus 1. So all we need to do here is use our product rule of exponents, which states that we can add, if we have two of the same bases multiplied together, we can add the exponents. So 2 more steps. This reduces to p times 1 plus I to the power of 1 plus n minus 1. Right? All we did was add the exponents. 1 plus n minus 1. And now if we reduce that exponent, 1 minus 1 is 0, and we're just left with n up there. So this is the amount. This is the amount in the account, or if you're talking about an account, this is a general term. But this is the amount in the account after n compounding periods. This is the nth term, the value of the nth term. Okay? It's the amount in the account after n compounding periods. Which also means that we can rewrite this because t of n corresponds to a. You can say this is a equals the original principal times 1 plus I to the power of n. And this is our main formula for the amount of a compound interest investment or loan, where P Give a bit of space. I don't really have any space, but you hopefully do. P is principal. I is the annual. Sorry, nope, don't say annual. I is the interest rate per compound period. And N is the number of compounding periods. Okay, let's apply that formula that we just derived. Example 1, calculate compound interest. To buy a new guitar, Gaston borrows $650, which he plans to repay in 5 years. The bank charges 12% per annum, compounded annually. So they're going to charge 12% per year, and they're going to compound it once each year. That's a very high borrowing rate, but it's pretty generous on it doesn't compound very often, it only compounds once each year. So our first step is to determine the amount that Gaston must repay. So he's going to repay it at the end of 5 years. Does that make sense? He's not repaying it over the whole 5 years, which you would do in real life probably if you finance something. He's saying, okay, I'm borrowing $650, and at the end of 5 years I'm going to give you everything that I owe you. Okay? Here we go. We know some things. We know that the original formula that we want to use is A equals P in brackets 1 plus I to the power of N. Okay, this is our formula for calculating the amount that he will owe. What do we know? Do we know the original amount? Yeah, the original borrowing amount is $650. So P is $650. Do we know the interest rate expressed as a decimal? 12%. 0.12. And we know the number of compound periods? Alright, sub in what we know. 650. 1 plus 0.12 to the power of N, which is 5. In my notes, I would just kind of reduce this bracket to 1.12. And then in my calculator, probably the fastest way to do this in your calculators is 1.12 to the power of 5. And then multiply that number by 650. And because we're talking about money, we're going to use 2 decimal places. Nice. And we finish it off. Gaston must pay $1,145.52 after 5 years. That's pretty steep for a $650 guitar. Gaston is pretty dumb. Okay, so now what's interesting to find out about, in this case it's pretty straightforward, but we want to find out how much interest he's actually paid. So in B, how much interest will he have to pay? Well, if A equals P plus I, then I must equal A minus P, right? You just subtract P from both sides. So the interest that he pays is the amount that he owes, which we decided was $1,145.52, minus the original amount, which is the cost of the guitar. And it turns out that Mr. Gaston is paying $495.52 just in interest. Yikes. What's really cool to see is if you calculate a mortgage, for instance, actually on Excel, I just found this out yesterday, they have a really good template for calculating the amount of a mortgage. And you can see exactly how much interest you're going to pay on that mortgage. You can also see, like, over the course of 25 years, if I put in an extra $5,000 next year, how much that ends up saving me just in interest charges is like hugely significant. So it's interesting to play around with that. Maybe we'll look at that after, just so you can kind of see what this compound interest really does to the amount that you owe somebody, especially if you're talking about the mortgage on a house. Okay, let's tackle C. I'm just going to slide over. C. Compare this to the amount of interest he would have to pay if the bank charged simple interest. Okay, so still 12% interest, but this time simple interest, so it's not compounded. Well, the amount of interest used for simple interest, you can flick back to your previous lesson, but interest is just the principal times the rate times the amount of time that it's invested, or it's being borrowed, okay? So the amount of interest, we know the principal is $650, that's the cost of the guitar. We know it's 12%, we're going to calculate that as a decimal, 0.12, times the number of periods, it's 5 years, and if you do that all on your calculator, you get $390. So, if charged simple interest, Gaston will pay $390 interest compared to $495.52 with compound interest. So you can see that if you are borrowing, simple interest is better for you. If you're investing, compound interest is better for you. Okay? That's example 1. Vary the compounding period in example 2. So we're not going to do a full year compounding period. We're going to talk about what happens if you're compounding this thing semi-annually, or if you are, that's twice a year, or if you're doing it monthly, which would be 12 times a year. So financial institutions often use other compounding periods rather than annual. What will be the impact on the interest Gaston pays if the interest is compounded semi-annually and then monthly? And we'll kind of leave this in 2 columns. You have your first column is going to be semi-annual. Semi-annual, which means twice per year. Not to be confused with biannual. Biannual would be once every 2 years. Semi-annual, you're cutting in half. Bi means 2. Different related words, not the same word. And B, we'll look at monthly, which is obviously 12 times per year. Okay, first semi-annual. Well, what do we know? The number of compounding periods is doubled, but that means that the interest rate per compounding period is actually cut in half. Okay, pay really close attention. We know P is $650, but the interest rate, I, remember, is the interest rate per compounding period. In the equation, in the question, we were given the interest rate per year. Okay, so we need to take that interest rate per year and divide it by the number of compounding periods in a year. Okay, I'm going to make a note of that. So divide the annual interest rate by the number of compounding periods in the year. Yeah, is this making sense? So I is the interesting rate per compounding period. We're given the interest rate per year, and there's going to be 2 compounding periods per year. Okay, so our new value, I did 0.5, is that what you're talking about? 0.12. So our new interest rate then is 0.06. And our compound periods, the number of compound periods, yeah, there's going to be 5 years, but we're going to compound this twice each year. So our new value for n is 10. So here's our 3 parameters that go into our equation. The equation stays the same. A equals p 1 plus I to the power of n. And same way as we did before, we just sub those things in. So the principal is still 650, but this time we have 1 plus 0.06, but it's being compounded 10 times. And if we put that in our calculator carefully, we'll get the amount that he owes them is going to be 1164.05. Is that more or less than he owed under the original situation? Yeah, it's going to be more. We can actually calculate the interest that's paid. We need to do that. So the interest paid in this situation is the amount he's going to pay minus the original amount of the guitar. So 1164.05 minus 650. In this case, he's going to pay $514.05 worth of interest. Okay, so you can see how increasing the compounding periods, I guess decreasing the length of the compounding period, increasing the number of times it's compounded within a year is going to make it grow more rapidly. Okay? We could say Gaston will pay $514.05 in interest if compounded semi-annually. Alright, let's make a prediction. Monthly, is he going to owe more or less? He's going to owe more. Okay, let's figure it out. We know P, 650. The interest rate, what do I do now to find out my interest rate? Pretty much just read the red writing. Divide the annual interest rate, which is 0.12, by the number of compounding periods in the year, which is 12. So our new I is 0.01. What about for n? Well, it's now the number of compounding periods. We're going to do this 12 times each year, and Gaston's not going to pay them back for 5 years. So 12 times 5, n is now 60. Rewrite our formula, which you have memorized now, so that's good. A equals P, bracket 1 plus I to the power of n. Sub in what you know. So 1.01 to the power of 60 times 650. Check up here to see how you did. 1180.85. And we can calculate the interest that he paid on that, which is just the amount that he owes them, minus the original cost of the guitar. In this scenario, paying 12% interest charged monthly, compounded monthly, he's going to pay $530.85 just in interest. Okay, just to clean this up and help you see what just happened, we're going to make a little table. You can let me draw the table first if you want, and then you can see it. So we've got the compounding period. We have the amount measured in dollars. And we have the interest also measured in dollars. If he compounds annually, we said the amount that he will owe is $1145.52, in which case he will pay $495.52 in interest. If he has a borrowing rate that is compounded semi-annually, he will owe $1164.05, in which case he will pay $514.05 in interest. And if it compounds monthly, he will owe them at the end of 5 years $1,180.85, in which case he will pay $530.85 in interest. So you can see as the compounding period becomes shorter, the interest that he pays is greater. It increases. Your practice problems for lesson 7.2 are on page 433, numbers 1 through 11. Just applying the different formulas and probably comparing interest under different situations.